Good afternoon, guys. We are meeting once again. Power machines N6 air compressors. So our question for today, it reads: a three-stage reciprocating air compressor compresses 0.3 meter cubed of air per second from an intake pressure of 90 kilopascal and a temperature of 22 degrees Celsius to a pressure of 2 megapascal. Intercooling is complete and the stage pressures are in geometric progression for maximum efficiency. Our gas constant is given as 0.287, our CP is given as 1.005, and then our compression index is given as 1.3. So it's a three-stage compressor. So roughly, this is how our structure or three stages have to be represented on our PV diagram. Our pressure versus our volume diagram. So on the first question, they are saying calculate the power required to drive the compressor if the mechanical efficiency is assumed to be 90%. So the first important thing that we need to do, let us summarize what are we given on the scenario. So I'm using the textbook Yegner and Detroit. So we are on activity 4.3 page 161. So I will try to summarize what we are given. Let's just write the data of what we are given. So on the data, I can see we are given our three stages. So X denotes number of stages. So we have 3. What else? Our V of air is given as 0.3 meter cubed per second. And then intake pressure, which is our P1, is given to be 90 kilopascal. And then our T1 is given to be 22 degrees Celsius. We need to convert it to Kelvin. So we add plus 273, which becomes 22 plus 273, which we are getting 295 Kelvin. And then what else are we given? We are also given it is this pressure, it is delivered at a P delivery or our P maximum or our P F4, which is said to be 2 megapascal. So if we change megapascal to kilopascal, it becomes 2000 kilopascal. And then the most important thing, once again, which are given, there's an emphasis that says intercooling is complete and the stage pressure ratio are in geometric progression. In other words, the pressure ratio are in a geometric sequence. When you get your P1, your P2, you see how this whole concept of geometric progression or sequence transpires. Now, by mentioning that intercooling is complete, you must always remember once a statement says intercooling is complete or intercooling is perfect, or if this question says minimum conditions prevail, minimum conditions prevail. In other words, if you check on your formula sheet, there are 2 formulas for calculating your power or for your work done. So which is to say, by mentioning that intercooling is complete or intercooling is perfect, therefore you must choose your formula for work done or for power that shows the number of stages. Which is to say, our formula now becomes, we are looking for power, we are going to say, therefore, power equals to xn over n minus 1 times our P1 VA into our P delivered divided by our P intake, close your bracket, to the exponent of n minus 1 over x n minus 1. So on this formula, on its own, there's a lot of work which you must remember. Every time you see that a question is saying intercooling is complete or perfect intercooling or minimum conditions prevail, therefore you must remember that the formula that you're supposed to use, it must show your stages at these two crucial points, this point and this point. Please, you must show those number of stages. If you do not show those stages, in other words, you are saying intercooling is not complete or intercooling is not perfect. So very important, you must remember, once they say intercooling is complete or perfect, you must then show the number of stages. So let's go together here. Number of stages, we said it's a 3-stage, so it's 3. Our index of compression, it was given as 1.3. Our index of compression, it was given as 1.3 divided by 1.3 minus 1 times our P1. Now we have a challenge. Is our P1 is given, what's our P1? Which is given as 90. Our VA is given as 0.3 times our P deliver. Our P deliver, that's our P4, which is our P4. It was given as 2000 kilopascal. Remember, it's 2 megapascal, so we converted megapascal to kilopascal. Our P1, we said, is given as 90 kilopascal. So for a complete cycle, we need to make sure that we have our P2 as well as our P3, or the stage pressure ratio, which we mentioned to be in a geometric sequence. They need to be shown there. So let's go together here. Our P delivery, we said, is 2000. And then our P intake, we said, is 90 kilopascal. And then our N, 1.3 minus 1 over our stages. Don't forget to show them. Is 3 stage times our N, which is 1.3 minus 1. So let's get our power. Let's get our P out. So we say 3 times 1.3 divided by 1.3 times 90 times 0.3 times our delivery pressure, which is 2000 divided by 90 times 1.3 minus 1 over 3 times 1.3 minus 1. So let's see what are we getting. Let's see what are we getting there. Okay, let me getting a small answer. Let me punch once again. 3 times 1.3 divided by 0.3 times 90 times 0.3, which is our volume, times our maximum pressure, 2000 over 90 to the exponent of 0.3 over 3 times 1.3 minus 1. I'm getting something like 94.55 996. So we can simply say 56 kilowatts. So we are getting our P out as 94.56. But the question says the power required to drive the compressor if mechanical efficiency is assumed to be 90%. Therefore, mechanical efficiency equals to power output over our power input times 100. Don't forget its efficiency. Our mechanical efficiency, we got it to be 90%, so we can divide it by, this one becomes 0.9. Our P out, we got it as 94.56 divided by our P input. So if we substitute here P input, let's see what are we getting there. 94.56 divided by 0.9. I'm getting something like 1 or 5.07 kilowatts. So that becomes our output power, or the power, rather our input power, the power required to drive the compressor. So the most important thing is not about getting the right answer, but the most important thing here is to remember the terms which are used in the exam. Very important term, you must remember this. If they say intercooling is complete or intercooling is perfect, you must know that the formula for work done or for calculating power which you are going to be using, it must show the number of stages. But if the question says intercooling is not complete or is not perfect, therefore we remove our stages and then you get your answer right. This is a very simple formula. Let's go to number B, or maybe before we go to number B, we can come back to this part where they say the pressure ratios are in geometric sequence or progression. Now, because we have our P1, we can get our P2 as well as our P3. Now, but the first stage which you need to do here, let us calculate our stage pressure ratio. So we can calculate our stage pressure ratio. The simple formula for us to use to calculate our K, or our stage pressure ratio, is this one. You just show your stages here and then your PD and your P intake. It's a very simple formula. Your maximum pressure, square root of your maximum pressure divided by our P1. Number of stages, let us show them. We are given a 3-stage. Our P delivery is 2000. Our P1 is 90. So let's get our P1, or rather let's get our stage pressure ratio. So we have 2000 divided by 90. I'm getting my stage pressure ratio as 2.8114. So that's our stage pressure ratio. Because of this emphasis that the stage pressure ratios are in geometric progression or sequence. Therefore, to get P2, what it simply means, P2 therefore becomes P1 times your stage pressure ratio. So P1 is our P1 is 90 times our stage pressure ratio, 2.8114. So times, we have 90 times 2.8114. I'm getting 253.026 kilopascal. And then our P3, therefore P3 equals to P2 times our K, which is 253.026 times 2.8114. So times 2.8114. I'm getting my K as 711.357 kilopascal. So now we have our P1, we have our P2, as well as our P3. So you can come here our P2 is 253.026 kilopascal, and then our P3 is 711.357 kilopascal. So we now have all our pressures. Now, another important thing, I think we'll talk about that one. I wanted to talk about the sequence of intercoolers, but we'll do it as we go to the question that comes now, which is number B. So let's go to number B. Number B, the question says, calculate the heat transfer into the two intercoolers per second. Now, on number B, our formula for calculating Q intercooler, but Q intercooler equals to X minus 1 times MCP into T2 minus our T1. So that's our formula for calculating our Q intercooler. So X, we said it denotes the number of stages. So if X denotes number of stages, in a simple way, you can simply remember that we have our P1, which is our intake pressure. So the pressure that comes after our intake pressure becomes your pressure in the first intercooler and the pressure in the second intercooler. So this is our first pressure in the intercooler, and then the second pressure in the intercooler. So we just have two pressures. Therefore, our number of stages, we said, is 3 minus 1. You can use this one for those who will be struggling to understand the number of intercoolers in whatever given question. And then times our mass. So we need to get our mass, but if you look at this question, we are not given our mass, so we need to calculate our mass. So to get our mass, we can use a very simple formula. I think it's fine. We can use a very simple formula. Let me calculate my mass at this point. So we can use this simple formula. P1 VA equals to MRT. Because we have our P1, which we said is 90 kilopascal, our VA or our V1, it was given as 0.3, so we need our mass. Our gas constant, it was given as 0.287, so 0.287, and then our T1, we said it was 22 plus 273, which gives us 295 Kelvin. So from there we substitute, let's get our mass. So we have 90 times 0.3 divided by 0.287 times 295. So I'm getting my mass as 0.3189 kgs. So we are sorted. Now we have our mass, which in normal cases in the exam we can make it to be 0.32 kgs, unless if they say round off to a certain number. And then so we substitute, our mass is 0.32, our CP2 was given as 1.005 into, once again we don't have our T2. So to get our T2, we can use a very simple formula once again. Let's get our T2. So to get our T2, please allow me to calculate my T2 here, because it seems like we are going to be running out of space. So T2, we can use the formula. I think we are familiar with this formula for N4 or for N5, engineering science or power N5. So we can use this one. T2 equals to T1 into P2 over P1 to the exponent of N minus 1 over our N. So our T1, 295, our P2, we looked for our P2, we got a 253.026. Our P1 is 90, and then our N, it's 0.3, it's N minus 1 over our 1.3. So let's get our absolute temperature, which is 295 times bracket 253.026 divided by 90 times 0.3 over 1.3. So I'm getting my T2 as 374.5 Kelvin. So we come here, we substitute 374.5. Our T1, it was 295. So let's get our answer. So it's 2 times 0.32 times 1.005 times 374.5 minus 295. I'm getting my Q intercooler is 1.1344 kilojoules per second. It's kilojoules per second. Remember our VA, it was given as 0.3 meter cubed of air per second. So which is even the mass which you got here. We must not forget to emphasize that our mass is in what? In seconds. Perfect. Now, can we go to question number C? Number C, they want us to calculate our heat transfer in the water cooling, or in other words, in the water jackets. So Q water jackets. We have so many formulas which you can use on this one, but the simplest one is just to go to revision for N3, where the formulas of heat transfer and the heat rejected. That is engineering science N3, if we had a good teacher or a good lecturer. So Q water jackets equals to MCV into T1 minus our T2. Remember, during heat addition, it is T2 minus T1. But the emphasis here, water cooling. So therefore, for water cooling, it becomes T1 minus what? Our T2. In other words, when you're cooling something, at the end of the day, your final temperature, it has to be cold. You have heated a material, but because you are cooling it, if you put it in water or oil, therefore you expect that final temperature to decrease. Therefore, water jackets equals to MCV into T1 minus our T2. Our mass, we already have it as 0.32 times, but our CV, we don't have it, but we have our R, we have our CP. So we can come here, we say, but R equals to CP minus our CV. Our R is 0.287 equals to CP, which is 1.005 minus CV. So CV here, it becomes 1.005 minus 0.287, which is I'm getting 0.718 kilojoules per kg Kelvin. So we come here, we say 0.718. T1, it was 295. T2, 374.5. So let's get our answer. 0.32 times 0.718 times 295, rather, yes, minus 295 minus 374.5. So I'm getting my answer as minus 18.2 minus 18.27 kilojoules per second. So we are done on the heat transfer to the water jackets. Lastly, we are looking for the isothermal efficiency, which is number D. We are looking for our isothermal efficiency. So the easier formula to use to calculate our isothermal efficiency, we can use our formula, but isothermal efficiency equals to we can use isothermal efficiency, we can use a power required or our power input. So which is power input or power required divided by our actual power. So we can use that formula, power, isothermal power, rather power input divided by actual power. But we can also use isothermal efficiency equals to isothermal power divided by our actual power times 100. So if we are using isothermal efficiency equals to isothermal power divided by our actual power. We have our actual power, which we calculated initially. We got it as what? 105.07, but we don't have our isothermal power. So for formula for isothermal power, we can use that isothermal power equals to MRT1 ln of PD over rather P2 P2 over P1. So we can use this one, or alternatively we can use isothermal power equals to P1 V1. Remember, Boyle's law says P1 equals to V1 equals to MRT1. So we can remove MRT, we place it with what? PV, which is one in the same thing. So it's fine, we can use this one because we have everything already. Our mass, we got a 0.32. Our gas constant was given a 0.287. Our T1, 295 ln of our P2. P2, we got it as our P2, 253.026. And then our P1, it was given as 90. So let's get our answer, our isothermal power, which is 0.32 times 0.287 times 295 ln 253.02 026 divided by 90. So I'm getting something like 83.49. So it's 83.49 kilowatts. Let me just try to cross check whether I calculated everything well. 0.32 times 0.287 times 295 times ln of 253.026 over 90. Oh, so there's a small mistake which is here. In other words, our formula is P delivered, not P1. So which is this should be 2000. So our formula should be 2000. So isothermal power, yes, isothermal power, because our isothermal power, it takes place between this point and this point. So indeed we say MRT ln of P delivered over our P1. So we need to substitute that one, 2000. So let me see, what are we getting? 2000 divided by 90. What are we getting there? I'm getting 84. 84.01. So I'm getting my answer as 84.017 kilowatts. So we have our isothermal efficiency, or rather power. So we come, we substitute here, which is our isothermal power. It's 84.017 divided by actual power, which we said it's 105.07 times 100. So let's see what are we getting. We have 84.017 divided by 105.07 times 100. I'm getting 79.963%. So last but not least, let us recap. There are two things which I need to drive home here. Now, when you calculate your isothermal efficiency, we can use the same formula. Remember, formulas for power and work done, they are interrelated. Therefore, when you calculate our isothermal efficiency, you can also say isothermal efficiency equals to our isothermal work done divided by your actual work done, which is to say, when you calculate your isothermal power, you can use the very formula to calculate your isothermal work done. But don't forget, it's MRT1 ln of your P delivery or P maximum. In other words, we are using the ratio of our maximum divided by the ratio of your intake. So I'm going to do the second question again on air compressors. Let's meet next time. Thank you.